At this stage, I'm going to do something which is a bit courageous, if I can say so myself. I'm going to deviate from what Weinberg does in his book and do a slightly different thing. So let me first tell you what Weinberg does at this point and then explain what I am going to do and why I am going to do it. What Weinberg does at this stage is examine a particular sequence of Lorentz transformations, Poincare transformations, which is given by the following. U inverse lambda comma A. So this is the object which Weinberg investigates. In particular, what he is going to do is replace the U lambda bar A bar in the middle here by an infinitesimal Lorentz transformation, and using that investigate exactly how the generators J mu nu and P mu are going to change under Lorentz transformations. Now what I am going to do is a small change from that. Instead of looking at this quantity, I am going to look at U inverse lambda A, U lambda bar A bar, U lambda A. Of course, this is a very minor change. In fact, you would easily be able to recover one from the other just by replacing U lambda A by U inverse lambda A. So there is really nothing much of a huge difference between the two approaches. But the reason why I want to take a look at this object, this one, rather than what Weinberg looks at, is the following. Remember, what we are actually talking about when we talk about U lambda A is this. You start with an observer O observing a state and saying that the state can be described by this vector psi. Of course, the state can be described not by a single vector but by an equivalence class of vectors which we call a ray. All multiples of psi, at least all normalized multiples of psi, are in the ray, but we are picking one of them. This is what O would describe the state of the system by. And then, if you go over to a different inertial observer, so you go from O to O prime, that new inertial observer will describe the same physical state of the system by a different ray, and so by a different set of vectors. And what U lambda A actually does is that it acts on psi to produce a vector in this new ray. So when we want to describe the system according to O, we use psi. When we want to describe the system according to O prime, we use a state U lambda comma A psi. Now, whenever we make statements about observable quantities, we really need to bring in the operators as well and look at various things like expectation values of operators, or more generally matrix elements of operators. So let's say we are looking at an operator A. Both O and O prime are looking at the same operator A and trying to figure out physical properties associated with that operator and of course the state they are looking at. So O would be using a matrix element which could be something like psi comma A phi, where psi and phi are two different vectors describing the system. How would O prime describe the system? O prime would be using his or her version of psi, not psi, but U lambda A acting on psi, let's call that psi prime. The same operator, but a different phi prime which is U lambda A acting on phi. So this is what O prime would use. This is what O would use. O prime's version is this. Now psi prime A phi prime is actually U lambda A psi A U lambda A phi. And by using the definition of the adjoint, remember U is a linear operator, so its adjoint is defined in the standard way of linear operator adjoints. This is U dagger or U inverse. Remember, U is unitary, so U dagger is U inverse. So O prime has two choices. O prime can either say, all my states are different from the states as seen by O, not the physical states, but when I say states here, I just mean the vectors that are used to describe the state. So O prime might say, more precisely, all the vectors that I use to describe states are different from the vectors that O use. And I'm going to look at the matrix element of the same operator A with these new vectors. Or equivalently, O prime can also say, the states I will use will be the same as O, but instead of using the operator A, I will be using the operator U inverse lambda A, small a that is, capital A, U lambda A. So this U inverse lambda A operator U lambda A captures the way in which an operator changes when you go from O to O prime. Of course, when you see the operator changes, bear in mind that we are going to now use the same states, not the transformed states. And with these, and hence, this will capture the way in which physical observable quantities will change when you go from one observer to another. What Weinberg does, on the other hand, is that he actually looks at this quantity, which would tell you how the operators would change, not really under T lambda A, but under the inverse transformation of T lambda A. So he also gets expressions for how operators change under Poincare transformation, except that he has slightly unusual looking expressions for that. So I would like to avoid that, and that is why I am looking at U inverse lambda A, U lambda bar A bar, U lambda A. When I replace the U lambda bar A bar in the middle here by the infinitesimal version, which of course can be written down in terms of the operators J and P, it will tell us how J and P transform when you go from one observer O to another observer O prime. That of course is exactly the same as what Weinberg also gets, except that Weinberg gets it for the inverse transform, whereas this version will give us the change in the operators for the direct transform from O to O prime using T lambda A. In order to proceed, what we need to do is write this product of Poincare transformations as a single Poincare transformation, that is U corresponding to a single Lorentz transformation and a single translation. But before we get to do that, we need to figure out exactly what U inverse lambda comma A is. Now I'm going to show you this in two different ways. One, using the standard multiplication rule that we have already worked out. So let's say U inverse lambda A, this has to be a Poincare transformation, or U corresponding to a Poincare transformation to be more precise. And let's say it's U corresponding to a Lorentz transformation lambda prime and a translation A prime. Then U lambda A, U lambda prime A prime must be U corresponding to the identity, which means it must be 1 or U I comma 0. No translation and the identity transformation for the Lorentz transformation. Now, if you use the product rule for Poincare transformations that get worked out, this side is actually U of lambda lambda prime, lambda A prime plus A. And this, as we have said, must be U of I comma 0. So lambda lambda prime must be I, hence lambda prime the Lorentz transformation for the inverse that we are seeking has to be lambda inverse. And lambda A prime plus A has to be 0, which means A prime, the translation corresponding to the inverse Poincare, must be minus lambda inverse A. So the inverse of U lambda A is simply given by U of lambda inverse minus lambda A. Now, this is an important enough relationship, and that is why I am going to demonstrate why this is true in another way. This way is absolutely direct. You don't even have to worry about operators acting on Hilbert space here. Just look at the Poincare transformation itself. Under the Poincare transformation, x goes to x prime, which is given by lambda x plus a. I am just using the matrix version here. Of course, you could use the component version, x prime mu equals lambda mu nu x nu plus a mu as well. Now, when you look at the inverse transformation, all you want to figure out is how to get x back if you are given x prime. And that's straightforward. All you have to do is move this a to the other side and then hit with the lambda inverse. So you get lambda inverse x prime minus a, or lambda inverse x prime minus lambda inverse a. So the inverse Lorentz transformation involved here is lambda inverse, and the translation is simply minus lambda inverse a, as we have just found out. So both of these, of course, give you the same final result, which is gratifying, that at least it ensures that we have made no mistake here. Now, what we will do is use this to achieve our goal, that is, try to write U inverse lambda A, U lambda bar A bar, U lambda A as a single Poincare transformation. Well, this is U of lambda inverse minus lambda inverse A, as we have just seen. You can write down the product of these two Poincare transformations directly. Lambda bar lambda, lambda bar A plus A bar. And now you have the job of multiplying this Poincare transformation with this one. And that is easily done. You are going to get lambda inverse lambda bar lambda for the Lorentz transformation here. And for the translation, what you need to do is apply this on this translation and then add this translation. So you get lambda inverse lambda bar A plus A bar minus lambda inverse A. So I will just rewrite that translation slightly so that it will be easier to handle at the next step. The translation is simply lambda inverse lambda bar minus identity acting on the translation A plus A bar. So this is our general expression for general Lorentz transformations, lambda A and lambda bar A bar. Okay, you must have realized that I sometimes keep on saying Lorentz transformation where I really mean Poincare. But Poincare transformations are also called inhomogeneous Lorentz transformations. So it's not that much of a slip of the tongue. Now, in order to see how the angular momentum and momentum operators, the generators of infinitesimal Lorentz transformations, transform when you go from the observer O to the observer O prime, what we need to do is replace the U lambda bar A bar by an infinitesimal transformation. So that's what we are going to do next. So what we have is U inverse lambda A, U I plus omega epsilon. That's the infinitesimal transformation with infinitesimal parameters, this omega antisymmetric matrix, and epsilon, this column vector of infinitesimal quantities. U lambda A equals, well, what we need to do is On the right hand side, we need to replace lambda bar by 1 plus omega and a bar by epsilon. And let's see what I get from that. I get lambda inverse I plus omega lambda. Then you get lambda inverse. This is I plus omega, so minus I simply gives you omega A plus epsilon. Now what we will do is replace the expansion that we have for the infinitesimal versions of U using J and P. And if we do that, we end up with this thing on the left hand side, U inverse lambda A, 1. This of course is an identity operator on the Hilbert space. To first order in omega and epsilon, this is what you get. On the right hand side, you have to realize that this quantity is actually identity plus lambda inverse omega lambda. So the infinitesimal Lorentz transformation has changed from I plus omega to I plus lambda inverse omega lambda. Note that lambda inverse omega lambda is still an infinitesimal matrix because of the presence of the omega in it. Similarly, the translation has now become lambda inverse omega A plus epsilon, which is also an infinitesimal translation. So what we need to do is simply expand out the right hand side using a similar expansion as well, and you get identity plus I by 2 lambda inverse omega lambdas rho sigma element, J rho sigma, minus I times lambda inverse omega A plus epsilons rho element P rho. I have deliberately changed the dummy index on the right hand side from mu nu to rho sigma because we want the omega to have mu nu and epsilon to have mu as index. We will soon see how that can be achieved. In fact, before we go any further, let me try to simplify or at least explicitly write down expressions for matrix elements of lambda inverse omega lambda and lambda inverse omega A plus epsilon. Now, we need the lower row, lower sigma version for this matrix element, but it's easier to start with this one. This is according to the standard rules of matrix multiplication. Lambda inverse is rho muth element times omega's mu nuth element times lambda's mu sigmath element. Now, to proceed, what we need to realize is lambda inverse transposes alpha betath element is actually written as lambda alpha beta. Well, it's not just written that way. The basic property L transpose eta L equal to eta ensures, and this is something we have shown in a previous lecture, that lambda inverse transpose, which is of course L inverse transpose, I'm just using L and lambda interchangeably here. L inverse transpose can be obtained, elements of that can be obtained by lowering and raising elements from L by using the eta matrix. Basically, all we are doing is rewriting this equation as L transpose inverse is eta L, eta inverse. This eta has lower indices, it lowers the first index of L, the eta inverse raises the other index of L. Now, coming back to what we were talking about, this is lambda inverse rho mu. So, basically it's lambda lower mu upper rho. This is because of the transpose, the switch in the order of mu and rho. Omega mu nu lambda nu sigma. Now, but this, as you recall, is the upper rho lower sigma version of the matrix element for this. What we need is lambda inverse omega lambdas lower rho lower sigma version, which means I need to lower this rho. That's pretty straightforward. You could formally do this by hitting both sides by an eta matrix element and contracting with it. But all you need to say is I am lowering rho on this side, I would also lower rho on the other side. So rho comes down, but comes down as a second index. Now, we don't really want to leave mu downstairs at the same time, but there's a very simple rule. If you have a contraction where the same index is repeated, you can simply raise this one and lower this one, and that will not change anything. The point is, when you raise, you use the inverse eta. When you lower, you use the original eta. And the two things, eta inverse and eta, just cancel each other out. So, instead of ending up with lambda with two indices both lowered, what I will do is raise this mu to get something more familiar. Let me just write lambda nu sigma next to it. After all, these are just numbers, they commute. And lower the mu in omega to get omega mu nu. And of course, that has also the advantage that we actually have omega lower mu nu, which is what you also have on the left hand side. So that's what lambda inverse omega lambda's rho sigma th element is. What we need next is lambda inverse omega a plus epsilons rho th component with rho downstairs. I will not repeat the calculation all over again, but if you proceed along the same lines as before, you should be able to show that this is actually equal to lambda mu rho omega mu nu a nu plus epsilon mu. Armed with this, we are now going to simplify both sides or compare both sides of this expression, and using that we will try to figure out transformation laws for J and P under Poincare transformations. Let me just cut the clutter here a bit. Let's get rid of all this extra things that we wrote down to recall previous results. And then let's just push this up. This one as well. So these are the two things we need to use out here. So the left hand side here is pretty straightforward. The U inverse U hitting the identity just gives you the identity. And then what you get is plus I by 2 omega mu nu U inverse lambda A J mu nu U lambda A. This is exactly what I've been saying. This is the transformed version of J mu nu for the observer O prime. And then you have the transformed version for the operator P mu. So that was the left hand side. What about the right hand side? The right hand side is identity plus I by 2 lambda inverse omega lambda's rho sigma th element, which is this lambda mu rho lambda nu sigma omega mu nu j rho sigma minus I times lambda mu rho omega mu nu a nu plus epsilon mu. And now we are in a position to compare both sides and write down the transformed versions. To do this, first let's gather the term with omega mu nu and epsilon mu separately. You can of course consider a special situation where the omega is non-zero and epsilon is 0. That is, you consider an infinitesimal transformation which only has a Lorentz transformation without a translation. On the other hand, you can also have a pure translation without a non-trivial Lorentz transformation. So you could have omega 0 and epsilon non-zero. What that means is terms with omega and epsilon have to match separately in this expression above. So you have, considering just the term with the omega, I by 2 omega mu nu u inverse lambda a j mu nu u lambda a on the left must match I by 2 omega mu nu times lambda mu rho lambda nu sigma j rho sigma, that's what you get from this term, minus what you get from this term, which is twice, the 2 is simply because you have a half outside, lambda mu rho a nu times p rho. I'd forgotten to write the p rho at the end here. So, this is what you get when you just take the terms with omega mu nu. On the other hand, if you just take the terms with epsilon mu on both sides, what you are going to get is the following. Minus I epsilon mu u inverse lambda a p mu u lambda a, the transformed version of the momentum operator, must match minus I epsilon mu lambda mu rho p rho. So these are the two expressions that we get. From these, we should be able to figure out how j mu nu and how p mu transform under the Lorentz transformation. But there is a bit of a problem there, especially in the case for the omega mu nu's coefficient. The other one is easier, so let me just work that out first. What you get from here, from the second equation, is simply u inverse lambda a p mu u lambda a must be equal to lambda mu rho p rho. So under a Lorentz transformation, the muth component of p changes into lambda mu rho p rho, and that should not come as a surprise at all. This is exactly how the components of a 4 vector are supposed to transform, and that's exactly what is happening here. Momentum is a 4 vector, and the momentum operator corresponds to a 4 vector quantity. The way it transforms under a Poincare transformation is exactly the way a 4 vector is supposed to transform. Let us now take a closer look at the omega mu nu transformation rule, or rather the j mu nu transformation rule. Note that the transformed version of the operator j mu nu, u inverse lambda a j mu nu u lambda a, is on the left hand side, is contracted with omega mu nu. On the right hand side, there is something else which is contracted with omega mu nu. Now, can we directly compare the two sides and say that u inverse lambda a j mu nu u lambda a the same as lambda mu rho, lambda nu sigma j rho sigma minus twice lambda mu rho a nu p rho? The answer is we can't. The reason we can't do that is because omega mu nus are not completely independent. Omega mu nus, remember, are antisymmetric under the interchange of mu and nu, and if you have such a contraction, then you can only compare the antisymmetric parts of what you are contracting with omega mu nu. Whatever you are contracting with omega mu nu, if that has a symmetric part, that is going to vanish on the contraction. So you can have nothing to say about the symmetric part by looking at this contracted expression. In other words, if omega mu nu a mu nu is equal to omega mu nu b mu nu, you cannot claim that a mu nu is the same as b mu nu. All you can do is claim that the antisymmetric part of a mu nu, antisymmetric that is under interchange of mu and nu, must match the antisymmetric part of b mu nu. Now in the expression that we have written down, on the left hand side we have omega mu nu contracted with u inverse lambda a j mu nu u lambda a, and that thing is already antisymmetric under the interchange of mu and nu, simply because j mu nu changes sign when you interchange mu and nu. So there is nothing to worry about the left hand side. The right hand side, on the other hand, is a different story. So let's take this expression and rewrite the right hand side after interchanging mu and nu. So if you do that, you get I by 2 omega nu mu lambda nu rho lambda mu sigma j rho sigma minus twice lambda nu rho a mu p rho. Of course, omega nu mu is minus omega mu nu, so I can write this as minus I by 2 omega mu nu. And in this term, we will play another trick. We are going to interchange rho and sigma as well. Rho and sigma are dummy indices, so we can of course call them anything else, including interchange them. Now, if we do that, we get lambda nu sigma lambda mu rho j sigma rho minus twice lambda nu rho a mu p rho. Now, notice that if I absorb the minus sign inside, this expression is simply lambda mu rho lambda nu sigma. These are just numbers, so you can safely interchange them. J rho sigma, that's what the minus sign does to j sigma rho. Minus twice lambda nu rho a mu p rho. Actually, what we showed right now is this expression is already antisymmetric in mu and nu. So, interchanging mu and nu actually gave back the same thing. On the other hand, this term is, as it was originally, is not antisymmetric under mu and nu. And that is why you are getting a different expression here. But, since this one and this one are equal to each other, they are both equal to half their sum. So, you can write this as I by 2 omega mu nu lambda mu rho lambda nu sigma j rho sigma. You get twice this, then you are halving it, so you get just this much, minus sorry, I made a mistake here. The minus sign going in would have changed this to a plus. So plus lambda nu rho a mu minus lambda mu rho a mu p rho. You can easily check that what we have within the bracket here is antisymmetric under the interchange of mu and nu. After all, you have this term with nu mu, you have the same term with mu nu with a minus sign. So we have now recast the right hand side exactly as something which is antisymmetric in mu and nu. The left hand side already was. So now you can just match the two sides of the expression. So this gives us the transformation rule for the J mu nu operators. Now this looks pretty complicated, but if you break this up into what happens under a Lorentz transformation and what happens under a translation, then it's actually pretty easy to understand. If you just look at a pure Lorentz transformation, there are no translations, so A's are 0, then you just have this one term. Notice that J mu nu under the Lorentz transformation is a linear combination of J rho sigmas with two lambdas as factors, but that's exactly how a second rank contravariant tensor or a 2-0 tensor in modern notation changes. So all that this is telling us is that angular momentum, or what we will see is angular momentum in the future, essentially forms a second rank tensor, second rank antisymmetric tensor. On the other hand, if you did not have a Lorentz transformation, but just had a translation of origin, then the transformation rule will simply read as follows. Lambda mu rho, lambda nu sigma, etc. would have to be replaced by delta mu rho, delta nu sigma, and therefore the transformed version will simply be J mu nu, the original angular momentum, plus A mu P nu minus A nu P mu. In figuring that out, I have just replaced lambda nu rho by delta nu rho and so on. Notice that all we are saying here is that when you translate your origin, angular momentum components change, and this is something which would happen simply because angular momentum, at least in the classical physical situation, is R cross P. Changing your origin changes R, and therefore R cross P changes. And it changes exactly by this A mu P nu minus A nu P mu amount. This has nothing to do with quantum mechanics in particular. You would get exactly the same result in classical physics as well. This then are the transformation rules for J mu nu and P nu, the operators, under a Poincare transformation. Now, as I've already explained before, I've deviated from what Weinberg actually uses here. So just to compare, I'm going to write down the result that Weinberg obtains by following steps which are very similar to what I have done, except that Weinberg starts from U lambda A, U lambda bar A bar, U inverse lambda A. So replaces our U lambda A by U inverse lambda A. So Weinberg's results of the similar entity turns out to be this. U lambda A, J mu nu, U inverse lambda A. Weinberg's book actually has J rho sigma here. I'm changing that to J mu nu so that comparison becomes simpler. Is lambda rho mu lambda nu sigma nu J rho sigma minus A rho T sigma plus A sigma P rho. And his version of the transformation rule for P mu is the following. Now, if you look at the second of the two equations, it's actually easy to see what is going on here. Instead of the vector transformation coefficient lambda mu rho, you are ending up with the covector transformation coefficient, which actually confused me quite a lot when I first met this. Exactly why should a true blue covector like P upper mu pick up a covector transformation coefficient? Then I came to realize that actually what Weinberg was talking about is really a inverse transformation. So basically these are inverse transformation lambda matrices sitting here, and that is why you end up with getting something which looks exactly like the covector transformation. After all, a covector transforms exactly in the opposite way as a vector, so that the result of a covector acting on a vector gives you a scalar. The two transformations cancel out. If you look at the J mu nu transformation, where something very similar happens, instead of the vector transformation coefficients, two of them sitting in front of J rho sigma, here you have two covector transformation coefficients, once again because of exactly the same reason, because this is the inverse transformation really that Weinberg is talking about. However, these terms look a lot neater in Weinberg's version, with two lambda factors sticking out and so on. This one looks a bit more complicated than that, at least. Doesn't really look as neat as that one. And it may be a bit difficult to realize that we are actually talking about the same thing. After all, the coefficients with AP here have two lambdas. Here on the other hand, you have only one lambda. If you think about this a bit, you would realize that the inverse transformation actually has a minus lambda inverse A. And that lambda inverse here is actually cancelling out one of the two lambdas, so you end up with only one lambda here. It could be a good exercise for you to check that if I were to use the inverse transformations explicitly here, this will become exactly the same as this transformation. So the final result essentially is the same, except that they look slightly different on the face of it.